We have 3 types of panels. Panel type A, because the performance is best, so we call it type A. It is a multi-layer design with flexible mat, aluminum plate, and then polyester fiberboard. Currently, we can make it 7 meter height. The density is 4.4 kilogram per meter square. And then we have 23 dBA insertion loss measurement result. And then we have a type B panel. Type B panel is the future. We will spend time on to improve it. It is a 2-layer of flexible mat separation by 100 millimeter. Because this separation, we can make a lightweight panel and still achieve a very high insertion loss. Okay, it is reduced the panel surface weight to 2.6. This is very important because a large barrier, if you count it, then you find this we have to reduce it. Otherwise, it is not handled by man. Then the third type is air tip, plastic air tip. Is very lightweight, but the performance is not good. It's only give 11 dB reduction. Actually, it would be better, but because for this project we do not have sufficient time to test it, and we got 11 dB approved by the authority. Okay, let's see the panel. This is the Type A panel. You can see flexible mat, aluminum plate inside it, and then polyester board. It can handle by 1 people, and each panel is around 7 kilogram. So if 4 together is 20 something, 5 together is more than 30. So when we need to push up this panel, it's quite difficult. Type B is 2 flexible mat, separation at 100 millimeter. This type of design we think have highest potential for further development. We can change each mat to different density. We can add material inside the between the 2 barrier. So when it opens, it is different from the others. The previous one, when it opens, it is at the edge, like a door opening, a 1-lip door opening. But this is look like a double-lip door. It opens on both sides. So the opening is at the middle of it. With this design, it is more easy to push it upward because the center of gravity of the panel is in the middle, close to the pole, so it's easier to push it up. When you see the video, you find that it is quite hard for the worker to push it up because the weight is blocked at the pole. The weight is off the pole. So, then also when it opens, the clearance for opening is half of the previous one. The previous one, we need 1.3 meter clearance, but this is only 0.65 meter clearance. Okay, the third type is the plastic air tip. This is just air tip. You can see the photo later. This is the it can hold by 1 people. This panel, entire panel, is only 1.6 kilogram. And okay, then this is the spectrum or the insertion loss of the feed type of panel, and we got 23, 20, and 11 for this feed type of panel, and we found that there is a dip there. This is 1,600 hertz. What happened at 1,600 hertz? Why they have this dip? It is suspected that this is the half wavelength of the sound, because the wavelength of this sound is around 200 millimeter. 100 millimeter is half wavelength. It would set up a standing wave, and the standing wave would making the noise transmission is easier. So for this reason, I think we can have something to make this a better performance. Okay, then for the structure, we do finite element analysis and then test on site. So the first of all is the carbon fiber pole. This is the long carbon fiber pole. And we are doing a worst case simulation, wind speed 40 kph, 7 meter height. Actually, it opened at 35 kph. So this is worse than actual. And the pole thickness is 2.6 millimeter. The simulation result showing this location at the bottom connection. This is the water barrier, the base frame. Then this is the connection. The connection have highest strength, and the value is 170 megapascal. For the yield strength of carbon fiber is 210 around. So it's too close. It's too close. So although it's worst case simulation, it's too close. So we increase the thickness to 3.5 millimeter. And the other element is the supporting neck. The neck there, and there is a wire to push it up, to pull it, in order to. Then when the wind blow on it, it creates a stress there. The string is 135 megapascal. Normally for steel, it can easily achieve 200. And this is the conservative simulation. We assume there is no friction. Once the friction on the ground, it will reduce the string by half. So this is, I think, is enough. So if not enough, we just increase the this leg to thicker steel.